Ahmed. He's the founder and CTO of NanoOps Inc. And Ahmed is going to join me in a second. But this is, I think, also a very unique and a very innovative approach to printing at the micro and the nano scale, particularly with the ability to handle wafers for electronics and advanced packaging.
Hi,
Welcome on the stage.
can you hear me?
Nice to see you. Yeah, I can hear you. I can see you very well. Always a pleasure to see you.
Yeah, good to see you too. I was at Munich Airport when was talking to Christoph yesterday. So, so I was
Wow.
between everybody's communicating through airport lounges or near the gate. So let me since we don't have a lot of time, let me share my slides. So I'm going to talk about a new technique that is high throughput micro and nanoscale printing of electronics and advanced packaging. Um, and I'd like to thank Masood because he was talking about his technique that does not use any nozzles. We also do not use nozzles, for example. So we use a technique called directed assembly of um, nanoparticles to make electronics and devices and components. So I'll talk about some of them very quickly here. So basically, our vision is a semiconductor foundry in a box, and we're not talking about just printing PCB or printing simple board or simple lines. We're talking about printing, basically replacing a clean room. And so, for example, you can actually build devices in a few hours. There's no etching, chemical reaction, or vacuum involved. It is secure, of course, because you have your own, as you can see here, this is a clean room. This is, I think, a Samsung clean room. And basically, we can do everything you can do in the clean room in a simple, fully automated, very compact system, like you see here. We call it semiconductor foundry in a box. It is about 100 times less cost. It is 100 times faster than conventional fabrication. 1,000 times reduction in materials, and also it's about 1,000 times faster than inkjet-based systems. And we demonstrated that the technology works down to 25 nanometers and can go to hundreds or thousands of microns as well. But our focus now is not on devices, although we can make devices. Our focus is on chiplet and 3D heterogeneous integration of electronics. As you know, nowadays, the more law is basically done at the 1 nanometer scale, and you can't get much smaller than that. And companies are moving to replacing the monolithic chips into a piece of silicon with lots of dies and that are interconnected. And so there's a lot of work now at Intel, Samsung, TSMC, and so forth. And that actually increases the yield and makes it simpler and much cheaper. The problem is that the lines and the interconnect that are needed for this are, and the microscale, less than 10 micron, and many of them are 2 micron, and some of them are submicron. And so as a result, all of this is done in a fab, same fab that you make the chip in. And so it cannot be done with companies like ASE or Amcor and companies that do packaging. And so what we designed here is this chiplet that we're focused on. In our machine, basically, you can apply the GDS file that has your design, multi-layer design, and you can basically additively manufacture and print micro and submicron interconnect. You can print passive components onto silicon sapphire glass organic substrates. We are adding the active components to the machine in the near future. And so how does it work? So you all know what the inkjet working mechanism is. Basically, you have droplets that's full of particles. You deposit, and then and these droplets make up your line, for example. And so your line is limited to the size of your droplet. Your resolution is limited by the size of the droplet, but also the alignment is limited by the mechanical movement of the nozzle. What we do instead is we basically direct particles, individual particles that are down to 3 nanometers in scale, in size, and these are, and we pre-treat the surface, and we apply either electric field use electrophoresis or use dielectrophoresis.